let's just get through this, because honestly I'm not feeling very well, but we're going to get through this. Let's just go. First question. Right, recall that's context-free grammar is G4, example, whatever. Convenience will rename its variables for single letters, whatever. Give parse keys and derivations for each of the following. So A is only occurring in this rule. So it's like F gives A, that's the only thing possible, and T gives F, and then E gives T. So this is easy. It's just the parse tree is something like E gives, T gives, F. Yes, right, because T can give F, and then F gives A, right. The derivation is even simpler. It's just E gives T gives F gives A, right. That's the 2.1a part. All right, uh, B is A plus A. Fine, so this should be easy, because plus is only happening over here, so that's the only rule that can generate it. And so we know that T can give A, because T gives F and F gives A. So we can just like sort of do this thing that uh, so E gives E plus T, but then that gives E plus T plus T, and that gives T plus T plus T, but then that can give so T gives F, right. So it's like F plus T plus T, and then this is, so you get the thing. Eventually it's going to derive this thing, A plus A plus A, and that was easy. So that's actually the C part. So B is pretty much just identical, so C is that. This is C. All right, what about D? This is also easy, because F gives this is the brackets only happen in this case. So these brackets must be coming from an F, obviously. So let's start from the inside. So inside you have an A. A is available from F only, in fact. So this is like F. That's what this thing is. So if I have to write this down, this is given by F, and then with the same brackets everywhere. So now, what is this? Like, how can you get this thing? Well, there is no rule for this, but F can be provided by E. So this is derivable from this, but then that is given by, so this is actually doable by F, but then once again that's derivable from this. This is, yeah, right. And then E is derivable from, well, it's a start variable, obviously. Cool. That looks, oh, so sorry, this should be this thing, which is given by F, but then that's derivable from E. So that's part D. So 2.1D is done. Let's go to the next one. Use the languages, these languages, together with example 2. Whatever. Show that class of context-free languages is not closed under intersection. So second question, A. So A is A power M, B power N, C power N, where M and N are bigger than or equal to. So these are like independent. Okay. Yeah, so that's a context-free language, we know that. B is also a context-free language, right, because it's just the, like, yeah, symmetric. Together with example 2. So intersection is not closed under, oh right, okay, I remember this. So the thing is that A power N, B power N, C power N, this language is not context-free, right, by pumping lemma and all that. So what that means is, just take the intersection, what we should get is just that, basically. So A is like done. B is use part A and D Morgan's laws to show that the class of contextual languages is not closed under complementation. So CFLs are not closed under complementation. Okay. Oh, right, because, well, okay, think about it. What's A complement? A complement is, well, okay, it's a fraction of that, right? So I want to show, yes, I just want to show that it's not, right? So assume that if it was, right, if it was the case, then what would have happened? Okay, this is sort of weird, isn't it? So intersection, huh? So we know that, okay, so if A and B are contextual languages, then A intersection B, that's not necessarily a contextual language. Yes. So I just want to be writing this as some sort of an intersection, and that should be doing it, right? Wait a second. Okay, Okay, wait. The negation is not. Okay, that's. How do I do this thing? Well, negation of A. I can just do it like, okay, so if negation of A was like context free, then that would somehow mean that something bad happens, right? How does De Morgan's laws come into play over here? Oh, okay. So just think about it. If it was closed under complementation, we know that A union B is actually closed under complementation, right? Well, since the negation is now closed under complement, so sorry, there's closure with unions. So if there's closure with negation, then that would imply that this is a context-free language. But then that's exactly just this thing. But then that's implying that two context-free languages, their intersection is necessarily context-free for like whatever languages you have, right? Yeah. So any arbitrary languages you take A and B, what you will have is that if negation is closed, then this quantity is a context-free language, right? So it belongs to CFL. But then that implies, well, once again, getting a negation of this whole thing that also is a CFL. But that means that A intersection B is a CFL for any context-free languages A and B, which is not correct because we know that it's not correct. So this is also done. All right, third part is answer to the following context free whatever. So this is the grammar that we have. Let's think about it. Oh, so there are no there are actually multiple rules. It's just all of these are concatenated in one. But let's like go ground up and let's see if we can go ground up. Actually just start answering questions. So A, what are the variables of G? I mean, it's pretty obvious. Everything that happens on the left hand side of any rule. So just R, S, T and X. What are the terminals of G? Oh, come on. So everything that is, not a variable and is happening somewhere in the rule, that's a terminal. So the only things over here I see are X, R, S, T, A, B, and okay, epsilon. The epsilon is just an empty string. So what that means is like A and B are the non-terminals. Sorry, they are the terminals. These are the non-terminals, the variables basically. C is what is the start variable of G. So a start variable that is so start variable has a special property that it can never occur. How do I say this thing? Actually, that's not quite correct. What I was going to say. So usually start variables are like on the topmost rule. So here I can just sort of say that, oh, it's going to be R. R is the start. So X cannot be a start variable because it's like, yeah, then what is all of this stuff even there for, right? So can T be the start variable? Well, no, but because then S would not make any sense. Like S gives this stuff, right? So what's even the point of having S if T is the start variable? Can S be the start variable? But then R wouldn't make any sense. So the only way this whole grammar makes sense is, it's like succinct, is if R is the start variable. And is also the start variable, obviously, because it's on the topmost rule, which is how it is. D. Give three strings in language of two. Come on. What is this stupidity? So let's just look at it. So X gives A and B, right? So it's something like A. And T, it gives X somewhere, fine. And S can give this thing. Okay. So, yeah, okay, that looks okay. So, okay, let's do it like this. So R, that gives S, that gives A, T, B. But now T can be a bunch of things. So T can be like, I don't know, it can be epsilon, it's just AB, or it can be AX, B, and then it can be AX, TX, and then T is once again epsilon, so like just AX, XB or something like that. Now just replace this X by A, if you can. So you just get like AB, AAB, and then AAAB. These are three strings which are in this language. Shouldn't be too hard. Cool. E is three strings not in language. Okay, this is slightly interesting. So now you gotta understand what this language really is doing. So X is like A or B, which is just representing terminals, in fact, some terminal basically. What is t? What does t generate? So t can give an epsilon, it can give an x, which is just some terminal. I mean, it's gonna devolve into a terminal eventually, and then it can give x, t, and x. Okay, right. But then that t can once again do the same thing. So okay, so can it give x and x? Because that's pretty much the only non-terminal, so the only thing that it can give, right? So yeah, it can. Can it give 3x's? Yes, I think it can, because obviously 4x. Okay, so I'm gonna just say that x power n is generated by t, and in fact this is the only thing that's generated by t, because there's only one thing to the right of this rule, which is x and t obviously, but then again t is gonna be replaced. So yeah, uh, so this can be the only thing that's generated, and this will be generated because, so just say x power n minus 1 is, you can sort of generate it. Well, yeah, so then you have this rule that t generates xtx, right? So you know that x power n minus 1 can be generated from this. Yeah, okay, that's actually not a good idea. Okay, so x power n minus 1 can be generated, and so can be x power n minus 2, it seems. So this is gonna happen. In that case, you can just replace this by x power n minus 1 or something. And so this just gives us x power n minus so n plus 1, that can be generated. But then so can be this thing, because and so you just replace it by n minus 2, then this gives x power n. So by induction it's gonna work out. But that is to say, that's actually gonna only happen if x and epsilon can be generated, which they can be obviously because of these two rules. And so what that means is like all odd powers of x and even powers of x can be generated. And so there you go. That means that t generates, well, basically sigma power n, right? Or more like sigma star. That's sort of a little thing. So t derives this. I shouldn't use this abused notation, but whatever. What about this? S gives ATB, BTA. Okay, so it's like A sigma star B, or B sigma star A, something like that. Okay, and so R also gives this. Okay, so just think about it. If it's gonna start with A, you can do whatever you want in the middle, but it has to end with B, and then you can start with B, but you have, so that's what S generates. What does R generate? R generate this thing x, R and x. So it's basically like, okay, and then R can, so it's like x and x, and then it's more R, and so whatever, it's like x power m R x, and then generate just replace that. So this is what R generates, but then S generates this thing. Okay, cool. So it's basically something of this form. It's all the strings which are of this form, or which are generated by regular expressions of these forms. Union, so sigma power. Okay, cool. Yeah, that looks correct. So the necessary condition over here is that there should be an A and then there should be a B. What if I can just like say all A's? Well, that's never gonna happen, right? So what does this mean? That A or A, that is not something that's in the language. Actually, A might be. I don't think so because of this rule. So obviously that makes sense. Next, F, right? True or false? T that gives us ABA. No, there's no rule like that. So no, it's false. And G is that T gives ABA. Oh, sorry, T derives ABA. Yeah, that's correct, because obviously, so this is true. And then okay, H is T gives T. There is no rule like that, so I don't think that's true, so it's false, I suppose. I think I is that T derive. That's I don't know quite, like, okay, so the way that we defined this symbol was that like there should be a sequence such that like you can have the yielding and then that's the derivation. So I'm assuming it's true. I don't know, I just have a guess it is, because there is a sequence, right? The sequence is this. So like yeah, it's probably possible. G. uh so XXX gives, you know what, I'm just gonna put this in the first page because why not. Right, so there you go. J is XXX, that derives ABA. It does, so that's true. K is X derives ABA. That is not true because X can only give one character. Like that's the only rule it has. So this is false. L, true, true. S can derive. So we just proved it cannot, in fact, right? Because it has to give this ABA stuff. So this is false. And then finally O. Okay, so that's a subjective question now. Give a description of. Okay, in English, I'm not gonna do that. I'm not gonna do that because this sort of stuff is not gonna come in the quiz. There's no subjective thing, so I'm just gonna move on. 2.4. 2.4a. Okay. Context-free grammars that generate the following languages in all parts. The alphabet sigma is okay. WC said so. CFGs. We wanna give CFGs that do this. Alphabet is 0 1. Okay, so W says that W contains at least 3 ones. Okay, this is a that's something you would do with the finite automata, right? Wait, wasn't there a theorem that you can convert finite automata with so like to context-free languages or something? I guess there was. In fact, you could convert push down automatas to, so like that should be doable. So how do you convert a DFA to something like that, right? Okay, so this is like probably doable with the DFA. So you just start off with something and then 1 and then you go. So 3 ones, right? So you have 3 ones and that's an accept state, and it doesn't matter, you do like 0 1 whatever. And with zeros, well, nothing much, it just does this thing. All these states as 1 2 3 4 whatever, or maybe like A B C D, just so we can deal with it like context languages. Okay, I don't remember what the exact thing was, but oh, I think it was like this. Okay, so all the strings that can be accepted starting from state A, let's just denote them as A. So those are exactly just the strings that right. So you gotta have a 1 first to move to state B, and then you have all the strings that can be accepted with that. So it's something like this gives, oh right, okay, I remember all of this. And then what about the 0 situation? Well, then it's like this. Yes. Oh, that's doable. Okay. So that's that. And then what else? B gives, so it's not B, it's A, because yeah, you have to put a 0, then you get back to A. So yes, that makes sense. Yes, so B gives 1C. So I'm just gonna push everything in like one rule, so just to make this clear, it's not a one rule but more like a combination of rules, but whatever, which is 0A. Then B gives 1C or 0B, then C gives 1D or 0C, but then D can only give like, okay, so D can give 0D or 1D or epsilon, because like obviously epsilon is something that is accepted once you are at D, or obviously. So yeah, it's the final state, it's gonna happen. So that's cool. That's A. That's a context-free grammar. Fine. B is W says that W starts and ends with the same symbol. Oh, this should be easy. It's something that you can do with, well, if your sigma is limited, yeah, I suppose you can do this thing. Right, this should be doable by DFA. So just start off at some state. Now the first symbol that you get, well, that decides what the ending characteristic is going to be. So just 0 and 1, right? Just starting off here, obviously. So in case it's 0, then like you reach some state. So like you do all the stuff that you do, 0 1. Not quite. Okay, so it's 0, so the start character is 0. Let's call this the 0 state, and this is the 1 state. Okay, more like 0a, this is 1a or whatever. This is just, I don't know, epsilon state, I don't know. And then okay, so this can go to the 1a state, 1b actually. This can go to the 0a state, b, sorry. With the 1 obviously, this is with the 0 obviously, so this goes back with 0, goes back with 1. What does this mean? Obviously this has to be an, starts and ends with the same symbol, right? So this is an except state, this is an except state. This is certainly not minimal, but who cares? Yes. What about the epsilon string? Does that start and end with the same symbol? I don't think so. So this is probably the thing. Oh, we want to get a context-free grammar, sorry. Yes, so it should be doable, I think. So it's like what? I can't just call this epsilon though. So let's call these states different things: A, B, C, D, and E, right? Or C, D, and E. So A can give no self-looping, by the way. So yeah, so you can give 0A, and you can give 0B, or 1D, and then B can give 1C, okay, and C can give 0B, and D gives 0E, E gives 1D, and just so you know, these are except states, right? So B and D, which means B and D can also give epsilon. Alright, that's the thing. Okay, next, C. And yes, I know there was a much easier way to be doing this context-free grammar, but I'm gonna do it like this because 2.5 is telling me to write everything as push-down automators. And guess what? DFAs are also PDAs, so it makes sense. W says that the length of W is odd. Once again, something that's easily doable with a finite automator. You start off with this thing, whatever character you get, 0 1, it pushes you to this, yeah, and then whatever character you get pushes you back. It should be easy. So it's like just two states, call them A, B, and then they go back and forth. This is an except, obviously. So this is 0 1, this thing is 1 0. Yeah, W is odd, obviously. So write the context-free grammar for this thing. A gives 0B or 1B, and then B gives 0A or 1A, or epsilon. Yeah, and that's easy. D is W says that the length of W is odd and its middle symbol is 0. Length is odd, middle. Oh, so middle symbol is something that's not. So you can't find this using what do they call it? Heck, I forgot. Using a DFA. So let's do it with a context-free grammar now. So okay, what are we gonna have? We're gonna have length is odd, middle symbol is 0. So just some start thing, and it gives like X and S and X, or 0, right? Because yeah, that's something that can happen. And then this X can give anything. It can give 0 or 1, right? Yeah, that looks cool, I think. So now we're gonna be doing this using a push-down automator, right? So first we'll have to convert this into a Chomsky form. Yes, I don't like this, but whatever. So this is like S gives Y and X. Yeah, or 0. Also, that's fine. Push-down automator are also just non-deterministic, so we can do it, no problem. What? Y gives X and S. X gives 0 or 1. And that's the Chomsky form. Chomsky normal form, yes. And it should be easy. So have something, push some special character, right? Don't read anything, just push some special character. Right, let's start doing this. So first, let's go with this rule. So if you're on the stack you have X, then once you read 0 or 1, well, you just pop off that X and go on, right? Yeah. So you can read 0 and pop of x and don't put anything over there, or you can read 1 and do this thing. Okay, what else can you do? You can, so if y is on the stack, then you can pop off y, and instead of that push x and s, right? Why is something look wrong over here? I don't quite know, but it does look wrong, doesn't it? I guess it's doable. So okay, so let's just do this thing. So you pop off y, right, and you put an x, I suppose. Heck, it's extremely weird actually. Never mind all that. Yeah, it's okay, it's completely okay. So what is I going to do? So just got, no, don't read anything, y, and then let's just put s in that, and then let's put, so once you reach this state, let's not read anything, not pop anything, just push x on the stack. Yeah, that should do it. Then this s thing, right? So yeah, you can either read 0, so like read 0, don't actually do pop s out, and then that gives this thing. Or you have another thing possible, that you don't read anything. Okay, this should be a two-state thing, right? So you don't read anything, you pop off s, and then you put x in there, and then you go back. So you do sort of, now you want to put y, right? So you don't pop off anything, just epsilon y. Yeah, that looks correct. So that's the thing. And then obviously this, so we don't read anything, you pop this thing out, and then you reach the final state. Yeah, that is the PDA for this. So there you go. D is done. What about E? E is, W is such that it's equal to the reverse, so it's a palindrome. Fine, so the context free grammar is easier for this thing. The PDA is probably not. Wait, how do I make sure that wait, what? So wait, okay, let's just do this thing, let's just do this thing. So you have the start, it gives x and s and x, or it can give epsilon, or it can give some character, or like x basically. Yes, x, that's wrong, because x will go into different things. That's not what we want. So it's 0s0, or it's 1s0, or sorry, 1s1, or it's one of those guys, so it's 0 or wait, so that's, yeah, that's pretty much it. So I guess so. So it's 0 or 1, or it's epsilon, right? These are the things. That's cool. I'm thinking this should be doable, right? Yeah, I think so. Never mind. So let's just do this thing. So s can give x0 or y0, or wait, y0 would probably not work, isn't that right? Oh, I guess we should convert this sort of. That's not going to be fine, but we can do a certain thing, which is, it's not the Chomsky form, but it's also going to work, right? This should do it. So start off at something to so I'm just gonna leave it like empty to indicate that we're not doing anything to the string or the stack, and just push this thing over there, right? You have this, all right. So first you got these guys, so I'm just gonna do that. So what do you read? You read 0 or 1, or epsilon in fact, and then you don't pop anything, and then you don't, yeah, pop anything, and then you push, more like you pop s actually, I think, yeah, and you don't push anything. Wait, over there, what was I doing? I was like pushing x. Yeah, that's okay, I guess that's okay. Yes, I assume that is okay. Okay, that's gonna work. What else? This thing. Yes. So heck, sort of weird, isn't it? Wait, so could I just do this rule directly? I probably can actually. And just think about it. You just know for sure that only when. Never mind. Just do this the traditional way. So you read 0, you pop off S, and then you put X over there. Easy. And then similarly, you can also read 1 and pop S off and then put Y. That's another possibility. And then finally, with the X and Y's obviously. So X is S0 and then Y is S and 1. Wait, what? I guess I messed up somewhere. I just don't remember. I can't do this. It's wrong. It doesn't. I will have to put X. Oh god, this is not good. So this is gonna get much worse. Not a good idea. Can't we do something better? Oh, let's try doing the GNF in a different. So let's try doing this thing instead. Okay, that's the rule. Where, oops, this wasn't supposed to happen. Here you have X giving 0 and Y giving 1. That should do it. So now it's going to be slightly different. So now, yeah. Okay, let's do it. So now you read and you, okay, input X. Yes. So you have read this. And then you also have to input S once again. Yes. So you go to some state and then you just push S on the stack. Yes, that's the correct thing to do. And over here as well, if you read 1 and then you push Y, obviously you like pop off S. So at this point the stack is now having like S and then beneath it at Y or X. That makes sense, right? That makes sense. Now these two rules, it should be doable. So you read 0 and then X and then you pop off. So yeah, or 1 X and then X. Alright, cool. What about this one? Well, just nothing and then and there you go. That's our final state. Yes, that's how it should be. Alright, next question. E is done. F, the empty set. For the empty set, the push down automata is like pretty easy. Just draw this circle and you're done, pretty much. Like there's nothing that you can do, so you're just done. So I'm not even gonna draw this. What else? The context free grammar, obviously. The context free grammar for an empty set. That's no grammar at all. As in the production rules are just empty. So yeah, I mean I don't know how to write that. It's just I know what to do basically. So I guess this is how I'm gonna write it. F, the production rules are empty. Yeah, that's cool, I think. Alright, 2.5. The informal description and state diagrams of the push-down automata for the language in exercise 2.4. I don't want to be looking for oh, that's just the thing that we just did, so that's actually done. 6th, give context-free grammars generating the following language. The set of strings over the alphabet with more A's than B's. A have to be slightly more than B. I'm just gonna put everything in the stack, right? Oh wait, we want a context-free grammar. Okay, this is still doable. So basically, just if you have something that generates equal number of A's and B's, that means you can generate something with more A's than B's, right? So now we are thinking of some grammar that generates, equal number of A's. Okay. Yeah, this should be doable. So what sort of thing could you have? So you can do this recursively. So let's just say that language is X, right? Yeah. So it can give, suppose its starting character is A, right? Then what should happen is that you have to have a B somewhere. Like eventually you have to have a B, at least one B, right? Otherwise it doesn't make sense. So you have B somewhere, but then these two, they should like add up their. Oh, that's kind of messed up, isn't it? Huh. Oh, so if you have a and b over there, that'll just be x. Yes. Or if you just have b and a, then that will be x. Yes. Okay. This isn't looking good. It's particularly not looking good, right? Uh, can we do something better? Let's actually try doing the opposite, as in construct a push automata and then construct the context free grammar for this, because I think the push automata is slightly easier. So we'll just put stuff on the stack, right? uh, Whenever you encounter an a and whenever you encounter a b, you pop off that. Yes. So you have this initial state, and whenever you encounter a, you just push it on the stack, and whenever you encounter b, you remove something from the stack. That is like something. Well, there's only one thing, obviously, a, so remove that. Also, you should probably have the start state like this, so it just doesn't read anything, do anything, just pushes this. Okay. Yes, this looks correct. Yeah. And at the end, like when the string is exhausted, now what's on the stack? A, right? Or nothing. So if it's a a, well, then you just trash it completely. If it's a dollar, you just, yeah, okay, that's probably the thing, right? So if it's a, you say, okay, put it into the reject state. This is accept state. Yes. It's just a epsilon. Sorry, it's epsilon a, right? Yeah, I guess so. And then it doesn't do anything, obviously. It just epsilon. And then at that point, it can just like keep going or something, like epsilon a. And then it's gonna like empty its stack or whatever. I also noticed, like, since it's non-deterministic and all, what could happen is that at some point it decides to switch over to this branch, but then again it doesn't like end up into an accept state, so that's completely discarded. So it's okay to do this thing. Yeah. What about this one? Why do I feel like I'm making this unnecessarily complicated? I probably am. It doesn't matter. That's an accept state, so just do dollar and yeah. Heck, do we even need a dollar thing? I don't think we do, right? Wait, okay, this should be the accept state. Ah, okay, we can just do the negation of that thing, right? Uh-huh. So at that point you feel, so let's just think of some language which is equal number of a's and b's, right? We'll just keep, oh, so if you have a dollar, okay, so you're gonna have three conditions actually. So I guess yeah, they want to do the PDA thing as well, but so yeah, I'm gonna draw the PDAs first. So then you also have, is it just easier to be writing context free grammars in the end? Maybe it is, right? I'm not very familiar with doing this stuff though. Writing context free grammars, I'm sure it's slightly more complicated than what I'm expecting. Okay, so this is going to be a language where you have more A's than B's. Okay, fine. So let's just think about it. At any point, if you're done with the thing, right? So just think about it. Like if you're done with the string, then you should probably be moving on. Yes. Oh, come on, think about it. How do you know when you're done with the string? You actually can't, right? That's bad. Just think about it. So in the end, what's gonna happen is that putting an epsilon arrow is gonna be a tragic story, I think. okay, so you can't put it back. Let's try to dismiss that, sorry. So you can't put a epsilon arrow because then it can like just jump over that thing and then that's gonna be complicated, right? Yes. But what I can put is an A arrow and a B arrow. Yes, I think. Ah, or I can just go back to the thing, right? Yeah. Like if you encounter another thing, just throw it away, sort of. So okay, let's just put an epsilon arrow and let's just see what happens. So I'm gonna put an epsilon arrow and see. So at this point you must have some A's in the stack, or it could be that you just read a B, and you read a B and there's nothing in the stack. So in that case, so first you just have 0 and A, right, in the stack. In that case, you get sent to the final state. Like this is just a final state. You're not gonna do anything. Now, what happens if you read a B and you encounter a dollar, right? Because in that case, you just reject directly. And from here, there's only one possibility, that is you can self loop, sort of. Yeah, that just happens. So you can leave the stack full, it doesn't matter. What is important though is that that if it encounters another input, then it's completely messed up, because now it's not gonna know what to do, and so it just has to stop reading, essentially. So I'm gonna say that if it encounters an A or a B, or well, just don't do anything to stack and just directly send it to this thing, because it is supposed to be the final state, right? This is the reject state. So yeah, like wait, okay, this is not correct, is this? It's probably not correct, actually. You pop off something from the stack. I mean, it's supposed to be one mode, right? Yeah. Once again, just assuming that um, something's not right about this. At any point, if it happens, but you don't know, because it could be like all the B's come first, and then you have all the A's. That's messed up. Alright, I need to find some other way to count this. As in, that you just have to start putting that stuff in there. I wish you could run both ways. Oh, you can. You certainly can. What am I kidding? So, yeah, okay. Right. So, you have this rule. At the same time, you can put another rule. As in, if you don't have anything in the stack, you just... Yes, you should probably have this rule, right? I don't know why this is getting so complicated. This shouldn't be that complicated. Especially in some with more A's than B's. Okay, so the push down automata is actually much more complicated than what I thought. Let's try doing the context-free grammar first. Yeah, I mean, that's probably the easier path. Just do the context-free grammar and then do the push down automata all the time. So first we need to have some sort of a language which has, okay, more A's than B's. Just to say that that language is generated by S. Okay, now you have cases. What if the first input is A? Okay, so what if the first input is B actually? In that case, this is so messed up. Okay, let's just think about it. You have a string which has equal number of A's and B's, right? The first few characters are A completely, and then you encounter a B. What should happen is that these characters, they must be equal in more like whenever you have equal number of characters, right? Okay, that's a really bad idea. We are not supposed to be doing this. I don't know how to write a context out of this. More A's and B's, or maybe like even equal number of A's and B's. You can't do this. How would you know if that's gonna happen or not? So everything's made up of these sort of things, right? A, B. That's not a good idea. Certainly not a good idea. Isn't for every A you have a B? Yes, but you also have B and B's combined together, so that's not gonna work. I can. I can't think of a push-down automata, and I can't think of a contextual grammar at this point. What the hell? Recursively, think of it recursively. If it just so happens that you encounter A on the first, then the remaining part, well, actually you don't know anything about it. Heck. Okay, so if it was like an equal thing, so you would have B somewhere, right? Like wherever you have it, and then these two should add up so that, yes. The number of A's and B's. Oh, so you kind of think about it like this thing. Okay. So suppose you have a string with equal number of A's and B's. The first character is somehow A. Okay. So what you will do is you will think, okay, so we have one more A. We need to somehow get an extra B from the remaining string. And so you will just think of, okay, so let's just say it's all equal at this point, right? So till this point it's like equal, and then you encounter a B somewhere, and then after that you have this stuff, right? So if this is equal, then this should also be equal, and you must encounter a B such that these two are equal, right? Yeah. This is extremely worrisome, actually. I don't know how to be doing this. Okay, so what if this was unequal? What if like there were more A's than B's over there? Well, then just add another B, right? So just keep going until eventually this does become equal. Because when this does become equal, then, you know, if this is A, okay, then we are once again in some trouble. Okay, then you know, still keep going. So it's basically like just keep going until this is all equal, and then you have a B, right? So you're just thinking of some language which has an equal number of A's and B's, and it ends with B, right? Okay. Equal number of A's and B's, and it ends with B's. Damn, this is hard, isn't it? Start slicing off stuff, maybe. Heck, maybe should be equal. What can I use over here? Okay, let's just leave it for some other time. Let's go to something else. Oh, it also has an answer, so I guess we can just put that. Okay, let's go with P. The complement of language A power n, B power n, so that n is bigger than or equal to 0. Okay, so on a contextual grammar for that. So essentially it's going to be like what? Oh damn. The complement is not going to be nice. I can do the language itself, but the complement is messed up. Oh, but I can do a push down automata. And the complement of that would be probably easy, because all I have to do is just, oh, it actually won't be easy, right? Okay, let's just think about it. So every time you encounter an A, so epsilon is probably also something that, so just start off at that. It's actually the accept state. I guess. So you start off at the accept state, because like if nothing happens, you just call it, or maybe don't start at the accept state. So start with the usual initial state, and then you just push this dollar thing inside. Okay, now you're in state such that yeah. So every time you encounter an A, you just push stuff inside, and every time you encounter a B, oh, so that was the language I was like describing before. That's problematic, isn't it? You yes, you just do this thing, right? Yeah, and then eventually you're just gonna have dollar on the stack. Yeah. And at that point we should not be encountering anything essentially. So the only possibility should be this, I guess. Yeah. Like if you cannot pop dollar, then that means you still have some A's on the top. Okay, and what if like you have exhausted it and then suddenly you have extra B? At that point you've got to do a reject basically. So you already have one reject state, and you know you're not ever gonna get the top. Okay, that's messed up because now you're gonna restart the whole thing. That's not good. So reject that with this. Heck, why am I doing this? I could have done a contested one. Never mind. So reject it with this, I think, B and a dollar. At that point, you just gotta reject it, right? Okay, that sort of makes sense. Yeah, it does. Now the question is, how do I convert this to a, context-free grammar? The negation of that. So how do you take the negation of this thing? Oh, that's a good question. So this is like where the stuff actually starts, isn't it? Okay, so something like this. Is this an accept state? I don't think it is. Wait, what? How do you know for sure? Oh, wait. So if this is the reject state, like okay, so it's A bar and bar. I see. I see. So every time you encounter an A, just keep going. Oh, so wait. You have encountered a bunch of B's. You cannot encounter another A. This is not. Oh, wait. What? What the hell? What if you encounter more B's than that? Oh, this is messed up. Messed up. You have to have two different states actually. So at this point, okay, you start off at this state. Every time you encounter an A, you push it inside. Pull. Okay. Then at some point you encounter a B, right? So you have popped off. Well, you actually don't have to pop off anything. Right now you go to this state, and every time you encounter a B, you sort of pop off an A. Alright, cool. And so eventually what's going to happen is you won't have anything to pop off, right? So I guess you should have this state as well. It adds a dollar for this thing. So if you ever encounter an empty stack issue, as in you don't have anything to pop it off anymore, at that point, although you probably won't, but yeah. Okay, so the number of, why is this so messed up? Okay, come on, think about it. So you probably also have to pop this off. It's actually in a, yeah, okay, right. This state initially, this is not a final state. You pop off A, it seems. Okay, this is wrong. I should have do this thing. So if you pop off A, yeah, you actually have to do this thing, right? Read A, put A. Read B, pop A. Yes. And then first time you read B, actually move to the second state, as in you can only read B. So if you ever read A, you know you're gonna crash it. Alright, cool. Now if it just so happens that your stack is empty, at that point, and you read B again, you still have to crash it. So if you read A, then eventually you just crash this thing. So if you read B, you crash it again. So that's a crash state. This is an okay, right. And you have this thing that if you don't have anything to read anymore, so epsilon dollar. And by the way, this is only going to be appearing when your like full A stuff is out. So don't worry about having to re-input stuff. So then in that case, you just put it into dollar state in a final state. Yes. I guess. Yeah, wait, so what if the whole thing is pop and now you encounter another B? Oh, that's messed up. Oh, so in that case, you can do this thing that, in that case, you actually send it to this. Right. Don't like pop anything, do anything. Just if you read B, send it to this, or in fact even if you like read A, you probably have to send it to this. Yeah, so just read B or read A, whatever, it doesn't matter, just send it. Cool. This looks like the machine that we want, right? Yes. So now the question is, we're gonna make a negation of this thing, right? How are we gonna do that? uh, this is not a wait, what the hell, that's a final state, is it? I mean, you can start the whole thing, yes. Oh damn, wait, but okay, so if you have an A, it does not know what to do, so it actually crashes itself by default. So yeah, that's okay. It's okay, actually. It's an epsilon. Yes, this is actually a final state. Cool. So now all you have to do is just make sure that this reads the full like, okay, it ends with the, yeah, it does not have that issue that it, after encountering an accept state, it's still gonna keep on moving. Just wait a second. Right, so the issue was that it should not keep on moving after you have encountered the accept state. Okay, as in at the last stage it should just accept or reject. Damn it. But I do have this thing, and that's a problematic thing. So I gotta get rid of this somehow. But how? Should I be wiser and do it better? I don't know. So epsilon dollar is this thing. So every accept state should be something that reads, right? As in, oh wait, it is actually, it's a read state, right? You have to read B or A to go to anything else. So you cannot just keep moving with, what do we call it? The yes. So once your input is done, you are pretty much done, right? Yes, I think so. Like, yeah. In fact, if you notice, all of these are read states, like except this one arrow, and there is not epsilon anywhere. Yeah, yeah, actually. And moreover, you also have this dollar thing, so that kind of confines a bunch of things. Hey, that's nice. So this is in fact a read set, and that's kind of the only thing that we really need, right? Oh, we also don't need this. This is an issue. N bigger than or equal to 0. I mean, n equal to 0, that case is kind of problematic, right? So we don't want epsilon, basically. Complement of that language. Well, I can do the complement of this language. This shouldn't be hard, right? Such that, n is strictly bigger than 0. I can certainly do a complement of that, but doing a complement of this particular language, where you okay, let's do it like this. So instead of this state, I'll say initially you just have this thing, it pushes the dollar into this, but now this is just a initial final state. Okay, that's a weird thing, but yeah. And what should happen is that after you read an A, it does this operation and goes to the first state. This is the 0th state first, and maybe this is the -1 state, I don't know. But yeah, this should be the push on automator now. Now the question is, how do we convert this to a context-free language? This is a very big one, and oof, I was not expecting something like that. So we got a push on automator for this thing, but how do we convert it to context-free language? Yeah. So what was the thing? It's like a sub pq that's equal to a sub pr rq if you have some r such that, well, yeah, basically for all sorts of r in fact, um, and you have a sub pq equal to, what is the transition from p to r if it's gonna just read something, well, I'm gonna put something on the stack, yeah, that's about right. So first we have to figure out the transition from this node to that node, right? Yes. And there's only two things, you can do this or you can do that, sort of. See, after you reach this point there's like no turning back, so turns out the only way to go from this to that. So actually let's start labeling these things, a b c d, and this is e, and this is f, right? So to go from d to e, okay, by the way, we need a complement of this whole thing, right? So we're just gonna do the usual thing, put these as the accept states everywhere, put these as the reject state, yeah, they should be doing it. Okay, so now to go from, this is so weird, what was the thing with the final state though, that I just don't remember. Is it to go from there to there, right? All the strings that take you from there to there, that does it. So if there was a single final state, which will make sense. Okay, I don't remember it. I just don't remember what the construction was. I have a PDA, but that's pretty much it. You know what? I think they are right. Building a context-free language is like much easier than building all of this stuff. But then for this, it's not easy, isn't it? Okay, let's actually not do it by the usual construction. Let's try doing it normally. The complement of this language. How I'm gonna do that? So a power n, b power n, so that n is bigger than or equal to 0. Without doing the push down automata. Wow, that's hard, isn't it? Yeah, just not this particular form. Oh, come on. Wait, is this a context-free language in the first place? The complement of that. I think it should be, right? When you've kind of... Wait, is this a context-free language? Context-free grammar for this. I mean, they're telling us to, so it must be. But how? How do I find it? What trickery is this? Okay, I think it's a good time we should look at the answers, right? But this doesn't make sense. This should be doable. W hash x such that WR is a substring of x for W and x in 0, 1 star. Let's try doing C instead. This is B. I have a push down automata, but I don't have context language. C is W hash x such that WR is a substring of x for W x in 0, 1 star. What? Substring of W. So substring of x. Okay. So x is some string. You have a hash over here. And then W reverse is a substring. So something in x basically, like, yeah, call this h. Then this thing is h reverse basically, right? Okay, so basically you just have to have some hash character, then some more characters, and then this palindromic sequence, and then some more characters basically. Cool. So let's just encode all of this inside an S. Let's put this inside something, I don't know, T. This is going to be encoded by T. Yes. And so this is just H, right? So yeah, so S gives x as x, obviously, and so just keep doing this. So this stuff is gonna like, I shouldn't say x s x, I'm just gonna say 0s0 or 1s0, sorry, 1s1, or it can give this stuff, so it can give a hash and then a t, right? Now should I be doing it like that? So I need that, right? So this whole thing will actually be generated by s in that case. So this is not the start variable in that case. So what I have to do is put r is st, so that you get this stuff. Now what's t? T is just t times t, it seems. Yes, I don't know, just put t0 or t1, or I don't know, 0 or 1, or you can just say epsilon. That actually works. Yeah, that looks about right. So that's the context free grammar. And okay, the push down automata is gonna be doable as well. So this was doable for some reason, or maybe I'm just not paying enough attention. Who knows? So yeah, so convert this to a normal form, obviously, right? I can convert this slightly differently. I can say it's like 0t or 1t or hash. That works. So this is already cool. What about these cases? So 1 hash t, right? Oof. I just do this thing. So it's basically like s gives 0x. That's not gonna be nice. Okay, let's convert it like this. So 0sx and then 1sy and 1zt, where x gives 0, y gives 1, z gives hash. That can be used to remove this whole thing. And so now it's in a good form, basically. Right? Yeah, let's do it. So you have something, starting variable, like push a dollar inside, whatever, it doesn't matter. Yeah, let's just do it. So r gives this thing, so whenever you encounter an r, you gotta put in the stack t, and then you gotta put you gotta put s again, and then go back, basically. Right, what about this one, this stuff? So whenever you encounter a t, first you read a 0 and then encounter a t, or you just push a t inside and then you can go back, essentially. Yeah, or you can have so encounter a 1 or a t and then a t and then go back. Yeah, or it could be that it's a hash, so in that case you have a hash and then a t and you just have an epsilon, basically, and that sends it back. Alright, what about this one? So if you encounter a 0, you start this whole sequence thing. So just push off s. Actually, don't push off anything, just put an x over there. And then you also have to put an s over there, right? I guess. Yeah. In fact, you can also do it with this thing. So 1s and then that gives y. Yes. I guess that's correct. And then you have this. So the last one is like 1z and t. So when you encounter 1, you can also do this thing. So encounter 1. Alright, and then also have to put a z. So just right, and then the usual thing. So if you just pop off the dollar symbol and go to the accept state. So that's the CFG. Sorry, that's the PDA, basically. So C is done. B is also done, except not really, but okay. Next is D. X1, X2. Okay, so all the hashes inside. Xi is AB star for some I j, Xi equal to X j reverse. Oh god. for some x. uh, okay, it's doable, it's extremely doable, isn't it? Fine, yes, we can do this, we can certainly do this thing. So let's do it like this. So for every xi such that this is not having it's something like reverse of it anywhere, you're gonna represent it by t. So you have this thing s gives, you know what, let's just start with r instead. So r gives so something 0 r 0, oops, or 1 r 1, or hash r. It's not r anymore, it's gonna be something different, it's t hash. Yes, right. Wait a second, just think about it. So these t things, what are you gonna do? So okay, I'm just gonna think that t things, they represent this stuff. It's like x1 hash x2 so on, without any constraints in this, right? Yes. I guess so. And so the start variable is going to be looking like this. You have this palindromic sequence thing, you have something before that, then this palindromic sequence thing, and then you have something after that. Yes, actually more like we put a hash in between, in fact. So just, yeah, that's better. Now what is t going to be like? T is like you just have some character 0t or 1t, or if you have a hash, heck, can you have a hash t? I think you can, right? Hash t. Can you have hash x1 hash? I mean, in that case, x1 will be something like, it can actually, because that's epsilon over there. Interesting. Yeah, okay, that actually makes sense, doesn't it? Okay, so what does r represent again? It represents hash, something in between. So it's like, okay, this stuff, then something in between, and then when it's this stuff, so it's like hash over there. That's what r is basically. Yeah, I guess that's right. You know what, okay, maybe these hashes are actually not necessary over there. Right, so it's either, so I'm gonna put some rules over there. So it since like, yeah, it can be epsilon, it can be epsilon, no issue with that. It's completely valid to be doing that, isn't it? Wow. It's going to be at some point. Fine. It's completely valid, right? Except maybe it's not. Except what if like this hash was not supposed to be there? Wait, why is this s over here? It should be r. I guess. So it can be actually just, you know what, just replace this by something. Let's just say it's either epsilon or hash t. So it's like x r y, where x can be hash t, or it can be epsilon, and y can be epsilon, or it can be actually should be t hash. Yeah, that's better. Fine, there you go. That's our context free grammar for t. And no, I'm not gonna draw the PDF for this, I'm too tired to be doing that. Alright, next, let's go to 7th question. Give informal English descriptions of PDAs as the language in exercise 2.6. Oh, okay, in this No, not gonna do that. It's already done more or less. Oh, can we go back to the first question now? Set of strings. So in 2.6, that is alphabet A B with more A's than B's. It's still a weird scenario. Okay. Think. Think why. Come on. What is it? Just why is it like that? There has to be some way. Just that's the reverse of that. Come on. Can't I do this? Fine, you just look at the answer in any case, right? So yeah. Let's go to 8th question. Show that strings the girl has two different leftmost derivations in number G2. I'm not going to do that. I'm not going to go all the way back to that grammar. 9th question. 9th is give a context-free grammar that generates the language. A is A, I, B, J, C, K. I is J, or J is K, where I think we've already done that, right? It's the union of these two languages. Oh, come on, come on. Is my grammar ambiguous? Yes, it is ambiguous. But, yeah. So, right. Generates this language. The start gives two different things, S1 and S2. S1 or S2, more like that. Where these generate the two languages. And it's a union of these, right? It's an OR condition. So S1 is just something that generates A power and B power N and M power C power M or something. So it's like what? It's just, so have this language concatenated with this. So let's just call this as T sub C in fact. And let's say this thing is RAB, right? So now RAB can give A and then B and RAB, or well, it can give epsilon. Alright, that works. They're not equal to 0, it actually does work. And then TC can give, there's only one thing it can do, it can give C and TC, yes, or epsilon. Okay. Yes, completely valid. What else? So the same thing is going to have happen for S2 as well. So S2 is just going to give us T sub A and RBC. Same rules once again. So T sub A gives A, T sub A or epsilon. And then RBC gives B, R sub BC and C or epsilon. Cool, that's our contextual grammar. Next, 9th is done. 10th, give an informal description of a push-down automata that recognizes the language A. I'm not going to do that, it's done, consider it done. 11, convert the CFG given in exercise 2.1 to an equivalent PDA using the procedure given in theorem point 2. Convert the CFG G4 to exercise. Okay. No, I'm not gonna go to G4. Convert the CFG G. Oh, come on. Wait. Exercise 2.4. Oh, 2.1 is this, right? Equivalent PDA. Wait, what? 2.1 is 2.1 is this exercise, right? And you want this to be pushed. I'm not gonna do that. Come on. Hey, I didn't answer if this is like ambiguous or unambiguous. So is this the S1 thing, is that an ambiguous grammar? That's a good question. Oh wait, it is obviously ambiguous because guess what? The epsilon string is present in both S, so it's generated by both S1 and S2, right? So it's ambiguous. Yeah. Cool. So it's ambiguous. Okay. 10th, informal description of whatever, not gonna do that. Convert the CFG G4 given in exercise 2.1 to an equivalent PDA using the procedure given in theorem 2.2. No way. Not going all the way back to 2.1. Wait, so anywhere else that you actually had the same thing? Page 103. This is page number 11. Okay, I'm not gonna do that. Fine, so 11th is done. I mean, considered done. More or less. 12th. Convert a CFGG given in exercise 2.3 to an equivalent PDA using the push procedure. Come on. 2.3 is what? 2.3 is this. Why do they want me to do it? I won't do it. Okay, I'm just gonna convert it to a Chomsky form, and after that, it's completely, you just know what to do it, right? So it's like, cool. So R gives, I don't know, X R1 S, R1 gives Rx S, right? Okay, that's S is not supposed to be there. Okay, I can just do it like okay, so it gives S, isn't it? Or S, that's, is that valid? I think it's valid. Like, you can certainly do this thing. You can think of it as, just, yeah, just, if you have R on the stack, you can replace it with S. It won't make any difference, essentially. Like, S is equivalent to R. Or more like R is equivalent to S. I don't know. I don't think that's right to think of it like that. Hey, so whatever is for S, I can just write that stuff over there. Why even bother with this? So I can write it as ATB or BTA. Yeah, that works. S is completely eliminated now. But now ATB, BTA, okay, this requires some stuff. So I can write it as, so it's XRX, right? Let's write it slightly differently. So I'll write it as R1 gives RX, right? So that I can replace this stuff. This thing I'll just break it into two parts. So I'll call this one as, I'll call it R2, I think. So R2, this will be R2, this will be R3, I think. So R2 gives AT, R3 gives B. Then again, I can convert this A to something else, like R4. R4 gives A. So for this thing, so this will be like R5 and R6. R5 gives R7 and T, and R6 gives A, essentially. Yes, and then T gives this stuff, so you can say this T gives T1X or X or epsilon. Or X is probably not a good idea, right? Oh, I can just replace whatever I see with X as A or B. Yeah, that's doable. But then that's gonna be messed up actually. Yeah, it's pretty much gonna be messed up. You can convert it into a slightly different thing as well. Epsilon transitions are, I assume they're allowed. So yeah, T gives XTX, which I can give as T1X or epsilon, and then T1 gives XT. So yeah, that's the thing, isn't it? So every rule has to be something like a terminal gives, so a non-terminal gives something A, B, C, whatever. And okay, so I guess the point was to remove the epsilon rules as well. Yes. Wait, how was that removed? I don't remember it. Alright, wherever you saw T, you could just delete this rule, and instead of that just put epsilon. So you would have something like S gives A, B, B, A, or A, T, B and B, T, A, where the requirement is that, okay, this epsilon rule is deleted. So that's how you convert to Chomsky, but I don't think that's necessary though. Like, you can just do it directly. I guess X gives A or B. That's okay. It's completely okay. Yeah, I guess this will be easy to convert to PDF. Fine, so that's 7th question done. 12th is done. Fine. fine. Theorem 2.2, I'm gonna skip over that quickly. Let G be equal to V sigma R and S be the following grammar. V is STU, sigma is this thing, and R is a set of rules. Describe language of G in English and prove that this is not regular. Okay, this is grammar is not regular. Fine. 0 and hash. Regular. Okay, cool. Pumping lemma, most probably, right? Okay, so S generates U and U generates. Okay, so it generates something like 0 U, so it's like 0 power n hash 0 power 2m. So, 2n. So, for all n, these things should be there in the grammar, right? Yes. Okay, that's not gonna help. I can't just prove it like that. Okay. It also gives T and T. So basically, what does T give? T gives, so it's like 0 T, just keep on going. A bunch of zeros, basically, like, yeah. Or hash. So it's hash union 0 star. That's what T is. So what is S giving us? S is giving us this thing, hash union 0 star, concatenated with hash union 0 star or U. Right, so it's a union between these two, isn't it? So all I kind of have to prove is that this language generated by U is not regular, right? Yeah, I guess. It's a union between these two languages, so I suppose it's okay. Right, so U is certainly a language which only has things, so it has things of only this form, right? And what that means is like it's actually it's not regular. So since it's not regular, hey, wait a second, let's just think about it. Everything over here actually starts with hash, doesn't it? No, it's hash union, so interesting. So you can have a hash over there, you can have a hash over there. I get it, I completely get it. So this is like stuff of, so this whole thing, this is stuff of the form hash 0 star union 0 star hash, basically. Like this concatenation always gives stuff of this form. What that means is, well, you pump this thing. Yeah, okay, that's almost sure. Yes. So consider n to be like extremely large, much larger than the pumping length. Then at that point you can pump this to get something like 0 power n plus k hash 0 power 2n. But notice that this is not present over here. It's just like, okay, this union U, obviously. So it's got to be present in whatever U generates. But what does U generate? Well, it generates this thing and it's not present over there. So there you go. By pumping lemma of regular languages, by the way, this is not regular. Alright, cool. That works. Describe this in English. I'm not going to describe it. Move on. Convert the following into equivalent CFG in Chomsky normal form using the procedure given in theorem 2.9. Okay. So first we need to somehow delete the epsilon arrows, right? Just do substitution, right? It's like, okay, A gives B a. Hey, wait a second. So B can only give you 0, 0. Oh. It's okay. You write it as x times x, and then x is just 0, so that works, I suppose. So B equal to epsilon is something that you want to avoid at any cost. So it's like BAB or B or epsilon or okay, so A is a start variable, this being equal to epsilon. I guess that's allowed. Start variable being equal to epsilon is actually allowed, isn't it? Like, how else are you going to? Yeah, I guess that is allowed. Right. I think so. So it's B A B B or epsilon, or so if B is epsilon, well then okay, this stuff is just converting to that. What about this one? This just gives us A. Okay, that's messed up, isn't it? Okay, that's actually sort of not good, so I'm just gonna remove that because obviously. Wait, so that doesn't give us a two variable thing, does it? It only gives us a single character. Okay, I mean that was redundant in any case. So yeah, so it's actually just replaceable by this directly, because if B was epsilon in any of the rules before, oh, that would be messed up. I get it. Okay, so yeah, so this can be written as A gives A1B or A2B. Wait a second. So this B is over there. Oh, you have necessarily put whatever was over here into that actually. So just A gives 0 0 A 0 0 or 0 0 or epsilon or something like that. Or okay, wait. So whatever is over there, we can just directly do that, right? Because we can get this thing. So everything that B can give, this can also give at that point. So it's like BAB or 0 0 or epsilon, right? And B gives this thing, and that's still better, isn't it? Yes. Once you can write this as this thing, A gives A1B XX epsilon, B gives XX, where A1 is BA and X is just 0, right? There you go, that's Chomsky form over there. That's how it should be. Next. Next is give a counterexample to show that the following construction fails to prove that the class of context-free languages is closed under star. That ABCFL that is generated by this, whatever. Add the new edge rule, but what new rule S is called the resulting grammar G. This grammar is supposed to generate A star. Wait, what? Closed under clean G star, right? This construction fails to prove that the class of context languages is closed under, but it is closed, right? Okay, but you just have to prove that this construction is falling. So the construction is let A be some CFL constructed by CFG, G, whatever. Add a new rule and call the resulting grammar G dash. The grammar is supposed to generate A star. Okay. Wait, S gives an SS, isn't it? Yeah. Wait. Under the star operator. I mean, this should work. Actually, I'm pretty much convinced this should work. What a counter example. What the hell? Start variable is this thing. Oh, come on. This should work, right? So whatever the start variable can generate, just put it in. Yeah, I mean, this should be working. Why does it fail? How does it fail to prove that? It does not. Like, by definition, a clean G star is like, so you have something from this language and then some content with something else from the language and so on. Everything of that form. And all of these can in fact be generated by S. So what's the big deal? I don't get it. And all of that can be generated by S gives SS. I just don't get it though. Why should it not be generating that? This is just stupid. Alright, I'm gonna move on to the next question. I hope this has an answer. And I'm sure this construction works. Okay, show that the class of context-free languages is closed under the regular operations, union, concatenation, star. The star is like easy. I'm just like did this thing. Actually, you can do a slightly better thing. You can say that R gives SR and then yeah, or epsilon. That sort of works. Or can you just say R gives S? Yes, that's better. And then S gives the usual stuff. Uh, S is the start variable for any language. So that does the clingy start. Okay, is closed under union. So okay, S1, S2 are generating some languages, and this rule makes the union basically. All right. The concatenation. So S gives S1, S2, where S1, S2 generate the two languages. This is easy. Use the results of exercise 2.16 to another proof that every regular language is context free by showing how to convert a regular expression directly to an equivalent context free grammar. What the hell? 2.16. Okay, fine. Oh, so a regular language is something that can be converted by a regular expression, right? Yes. Equivalent context free grammar. Oh, this should be easy. So let's just say that by induction, suppose that you know how to, I don't know, convert. So you have some grammar that so that actually expresses some regular languages, right? So S1, S2 are start variables of grammars that generate regular languages R1, R2. Then their concatenation, well, that's generated by this thing, right? The grammar with this start rule. Their any clingy star is generated by, well, this start rule. Their, what is it called, the what was I going to do? God damn it. The complement, right? That's actually a issue because a regular expression also has complements and it has subtractions. Okay, how do you express a complement? That's a good thing. I don't know. Like, context free languages are not close to complementation, so that's a messed up scenario, isn't it? Huh. Okay. So I guess we can just prove it for some of the base cases. As in, we're gonna prove that okay, this quantity and so is its complement. Both are in fact going to be like context free or something. That's probably not a good idea. So can I prove that if you have a context free grammar for some regular language, you also have it for its complement? If I can do that, then this is pretty much done, right? Because yeah, it's concatenation and union and the intersection, or the intersection as well, right? Although regular expressions don't have intersection, I don't think they have. Do they? They can actually. So I mean, it is close under that. Fine. So I just have to prove those extra things. I guess I'll do it later because battery down. But yeah, I'll see you guys in the next video. Bye.